Today we're going to take a look at exponential growth and exponential decay. We're going to start with an example of exponential growth. Here we have an antique chair, and it grows in value at a rate of 3% a year. And the chair was originally worth $250, so we want to know what it's worth after it's 100 years old. Now, you remember that the formula for exponential growth when it came to compound interest looked like that. And this is when the interest was compounded annually. So the formula for exponential growth is really exactly the same. We're just going to change some variables around. So P, our principal, would be our initial amount. We've got 1 plus whatever the rate of growth might be. And remember, 1 plus the rate is 100% plus the rate of growth, raised to the number of years. So if we substitute, we're going to have the initial amount of $250, 1 plus 3%, raised to the 100 years. And that turns out to be $4,804.66. Now when you put this in your calculator, be very careful and make sure that you follow the right order of operations, parentheses, then exponents, then you'll multiply by the $250. So you see here that after 100 years, a chair that was worth $250 would be worth almost $5,000. Now this is a graph of the function that shows the value of the chair over time. So this is y equals 250, 1 plus our 3% raised to the t, because that is our variable. Time is what's changing here. And you'll see just from the equation that we do have an exponential function. The exponent contains the variable. And you can see just from the shape of the graph, the way that it increases rapidly, that it's exponential growth. So we wanted to know the value of the chair after 100 years, and if you look on the graph, that's about here, which corresponds to about $4,800. So now we have an example of exponential decay. We have a new car that loses its value at a rate of 15% per year. The car is originally worth $25,000, and we want to know what it's worth after 5 years. So exponential decay looks very much like exponential growth. We start off with an initial value. We've got 100%, except instead of adding a rate, we're subtracting a rate. So this will be decreasing at a rate of 15% per year. So here, if we substitute, our initial amount is $25,000. We've got 1 minus the rate raised to the 5th power. So this would be $11,092.63. So after 5 years, the value of the car went from $25,000 to about $11,000. You should also take note that 1 minus 0.15 is equal to 85%, which makes sense here because if the car is losing value at a rate of 15% per year, that it would be worth 85% of what it was worth the year before. So this graph shows the value of our function over time. And you can see that it is exponential decay, the way that it decreases very rapidly. Now, the equation of this function would be y equals 25,000 times 1 minus 15% to the x power. So that equation is exponential because our variable contains, or our exponent contains the variable. Now, the scale on our y-axis is in the thousands, so this would represent 25,000, and you see at year 0, that's our initial starting time, the car is worth $25,000. And the question asked us about the value of the car after 5 years, and it looks like that's approximately $11,000, which is the value we found algebraically. So you have a worksheet with 5 problems, and for each of the 5 problems they give you the equation, so you won't have to come up with it for these exercises. But you should take note with each equation whether it's an example of growth or decay. Now here we've got our base is 1/2, and that tells us that this is a decay problem because 1/2 is 50%, so we're losing 50% of the mass of our radioactive element every 25 years. So for part A, they ask us for the initial mass. So what we need to do is plug in a value for t, and initially no time has passed, so we're looking at t equals 0. So we can simply substitute. We've got 10 times 1/2 to the 0 power. We know that 1/2 to the 0 is 1. So we get that the initial amount was 10 grams. So we're going to write that. The initial amount is 10 grams. Okay, now for part B, we'd like to find the amount present after 80 years. So we plug in 80 for time, and to calculate this we can use our calculator. We end up with 1.088 grams. So now we write our sentence. After 80 years, 1.088 grams are present. So we started out with 10 grams. After 80 years, we're down to approximately 1 gram. Here we have an example of exponential growth, and the base is actually e, which we learned was approximately 2.7. So now let's find part A, the initial number of fruit flies in the population. The initial number of fruit flies we find by setting t equal to 0 because no time has passed. So let's see, that's 0.03 times 0. We know that 0.03 times 0 is just 0. E to the 0 is 1, so we get 20 times 1, which is 20 fruit flies. So we write that out. The initial number of fruit flies is 20. Okay, now we're on to part B. We need to know the population after 72 hours. So again, we are substituting into our given equation. We need to find Q of 72. So now we have 20 E times 0.03 times 72. So this one will rely on our calculator, and we end up with approximately 173 fruit flies. So this means that after 72 hours, we went from 20 to 173 fruit flies. So let's write that out. After 72 hours, there will be 173 fruit flies. And now we'll take a look at the graph of Q. And here is our graph of y equals 20 e to the 0.03 t, and you can see that our initial value when t equals 0 we have 20 fruit flies. And then when t equals about 72 hours, we have approximately 170 fruit flies. At this point, you should pause your video and work on problems 3, 4, and 5, and come back and watch the solutions. So I will start with number 3 here. We've got bacteria increasing according to this model, and t equals 0 is our 1990. So if we wanted to find the amount of bacteria in the year 2000, we would need to substitute t equals 10, because 10 years have passed since 1990. So P of 10 is 2500 e to the 0.0293 times 10. And that comes to be about 3,351 bacteria. So we'll write that out. There were 3,351 bacteria in 2000. Okay, part B. We want to know the population in 2010, so that's 20 years after 1990. So we find P of 20, which would be 2500 e to the 0.0293 times 20. And that is about 4492 bacteria. So there were 4,492 bacteria in 2010. Okay, on to number 4. For part A, we want to find the initial quantity. In order to find that, we need to substitute 0 for t. So we end up with 10 times 1/2 to the 0, and 1/2 to the 0 is just 1. So our initial quantity would be 10. So they don't give us any units in the problem, so we would just say the initial quantity is 10. Okay, part B. Determine the quantity after 2,000 years. So we've got 10 times 1/2 to the 2,000 over 5730. So this gives us approximately 7.851 units left after 2,000 years. And that makes some sense, because after 5,730 years, we should be left with half of the initial amount. But only 2,000 years have passed, so about 7.8, 7.9 makes sense. So let's write our statement. We've got after 2,000 years, (7.851) units will be present. Okay, now for part B, sketching the graph, you can look at that on your calculator. Just make sure you set the window so that your x values go from 0 to 10,000. I would show you here, but I'm having some limitations with the technology that I'm using. Our last problem, number 5, is about inflation. And they tell us that inflation averages 4% over the next 10 years. And then they give us this formula where P is the initial amount or the initial cost of something. And you see here, here's our 4%, and here is our 104%. And T every year is our variable. So now, if we wanted to find the price of an oil change after 10 years, which was initially $23.95, we find C of 10, The initial cost is $23.95. We've got our 104% raised to the 10th power. And this comes out to be $35.45. So what this is saying is that after 10 years, an oil change that was $23.95 would be $35.45. So we write our statement after 10 years, an oil change will cost $35.45.